Welcome to this presentation, which I've chosen to call the ABC of game optimization. Actually, I just realized that the title is a little bit off. It should actually be the ABC of asset optimization. Now, my goal with this presentation, it's not to give deep technical rendering engineers something to think about after this presentation. So do we have any render engineers with deep knowledge about the rendering pipeline in here? Hands up in that case. One, okay. Two, okay, thanks. You two are gonna be a little bit annoyed with my simplification of a topic that's extremely difficult. My goal is to give artists, producers, people that have a limited understanding of how the rendering pipeline works, a little bit of idea why you do different things with 3D assets in your game. So let's jump into it. This is me. I just found out that I look a lot younger than I actually am. I'm crazy old. I'm 40 years old. I've been around for a long time in the games industry. Started as a gameplay programmer back in 2000. Worked on a couple of games with Starbreeze. Then I did a little bit of poker in between, and then I worked as a producer for Syndicate and Chronicles of Riddick, Assault on Dark Athena. Did a stint with Handsoft, and since about 2.5 years ago I'm working with Simplygon. Simplygon, if you haven't heard of it, we work within asset optimization. We consider ourselves being the gold standard for asset optimization in the high-end video game industry. Now, I'm not going to use this speech as some kind of sales pitch for us. This is the only time I'll actually mention what we do. But I'll go into the area of our expertise. This is a hamburger place that just opened down the road of our office. It's awesome. They make perfect burgers. It actually started like a food truck, just outskirts of the town. You had to take a car and you really had to know where it was. But they were so successful that they opened up a restaurant in the center. Now when I went there and when I was building this speech, I realized that actually a lot of the things that you do when you optimize a game is similar to what happens when you optimize a hamburger joint, and I'll tell you more about that. I'll get back to it later. So let's say like this. You're building a game. You have this concept. It's gonna be awesomely beautiful, a lot of details. It's the best looking game ever. Now you're probably using some custom engine, or you're using one of the off-the-shelf engines like CryEngine, Unreal, UE4, or Unity. Now the thing is that this is your render pipeline, extremely simplified. At one end of the render pipeline you have assets going in. And they go through a bunch of stages and then they end up on the screen. As you're getting towards the end phase of your project, you bang your head against the wall. You're trying to optimize the game to get it to run at your target frame rate. And as the deadline approaches and you really got to get the game out, you have to cut it down and remove art assets, reduce the quality to get it to run at your target 60 FPS. And what you end up with is something like this. Of course, extremely crude, but just to make a point. Now the thing is, as you were optimizing the game, if we look at this crude render pipeline, you have a couple of problem areas. There's 2 bottlenecks in this pipeline. But if you're optimizing here, no matter what you do to your game is going to gain you any more performance, because the bottlenecks are before where you're optimizing. So what we're going to do here is we're going to take a look at a generic render pipeline. Every engine is unique. Every engine has its strengths and its drawback. But if you look at a render pipeline from a high level, it is very similar anyway. For the example, we're going to use this simple architecture. I've chosen not to take into account several GPUs and things like that. We have one CPU with 4 cores, and we have one GPU. And if you're building a game for multiple GPUs today, you're still targeting a very, very small market. So this is a generic render pipeline. What we got here on the top row is a couple of cores working on preparing the next frame. Then you have one core working on sending draw calls to the GPU, who then rasterizes the draw call to the screen. And if we look at what happens in one frame, so basically if we're targeting 60 FPS, we got 16 milliseconds to do all the frame preparation. Basically calculate what's happening in this time slot. After that, when we're done with that, we will then start sending all the objects over to the GPU for drawing. Basically rasterization. In the meantime, the CPUs can go on and start working on the next frame. So we always have 1 frame lag, and actually a lot of engines would have more frames lag than this. Now, if we go back to that hamburger place, what's happening here is basically these guys, they're making fresh hamburgers. They're making like grinding meat, and then they're frying the meat, and then they're making the burgers. It's pretty much the same thing. It's 3 steps. You're taking meat, frying, and putting the burgers together. I'm going to get back more to how that's relevant for this. Now, in the hamburger place, it's not going to take 16 milliseconds. It's going to take a lot more. But we only got 16 milliseconds if we're targeting 60 frames per second. But we're in a hurry then. Luckily, processors can calculate a lot in this time frame. That just put 2 random float numbers up there, and they can do basically more than 1 billion times in that time frame. They can do that calculation. But there is a shitload we need to do for a frame. So let's take a look at what we have to do in each of these different segments. And don't leave yet. I promise I'm not going to go down to deep technical level there. I've actually run this presentation for my wife, who's in pharmaceuticals, and she kind of understood it a little bit. So, frame preparation. What do we do in this time slot? Well, we're going to calculate audio. I mean, right now I'm speaking here in this room with a lot of acoustics. This needs to be calculated. A lot of time we go down into that. We need to calculate animations, if we have animations. Not for rendering purposes, but we might need it for example, hit calculation if we're making a shooter. We need to make allow AI time if they're going to make any smart decisions. We need to calculate physics. We don't want stuff to fall through the world. We need to do weapons. Typically tracing and stuff like that is very costly. And then scripts, any game logic that needs to be run. There's probably more things, but these things are probably the ones that would consume most of the time. So when it comes to rendering a frame, basically what's happening here is that the CPU will tell the GPU what to draw by sending a draw call, 1 at a time. And the key here is to keep the GPU busy all the time, and I'll tell you why in a bit. But we need to go down to what is a draw call. Is there anyone here that's never heard the term draw call? Just raise your hand in that case. Okay, good. Draw call is a fundamental part of game creation. Basically what it is, if we're going to draw this character to the screen, what will happen then is that the CPU will create a state package, basically telling you, we're going to draw this character, and this is the information that we need to draw that character. This usually takes about the same amount of time every time you do it, no matter what you're drawing, with a little bit of modification there. But now, afterwards, the CPU will take that state and send that to the GPU, who will then draw that to the screen. It will essentially execute shaders to put that object onto the screen. The GPU will then access materials. In this case, we have a bunch of textures in memory, and we have mesh data, and we'll then apply the state to these objects. So it will take the object plus the state and put that onto the screen, like this, and then perform the shading. And after a draw call, in this specific instance, we won't have a complete object. The wireframe that's there, it's just there for visualization. But in this case, this object consists of many materials. And each draw call you can only draw one material. So this is what it looked like after one draw call. So what creates a draw call? Well, each object will consume at least a draw call. There are, of course, methods that you use called static batching and stuff like that, but just for simplicity, each object consumes one draw call. Another call, if we want shadows. Each material, after the first one, will add additional draw calls. So, for example, that character, she has, I think it's 8 materials, which means that she needs 8 draw calls. Particle systems, post effects, dynamic lights, and a lot of more things. So on the rasterization side, what will happen there, this is the GPU's side of the job, is we need to do vertex shading, basically all the points in the triangles. We need to do pixel shading, all the colors. We need to calculate lighting based on what it looks like in the environment. Post-processing, particles, shadows. So there's a lot of things that's happening here. So just a summary where we've gotten so far. The CPU tells the GPU how to draw what. The CPU side of things is a fixed cost, whereas the GPU actually depends on the complexity of what you draw. Some draw calls are extremely expensive on the GPU. And finally, as I mentioned before, for efficiency reasons, you want to keep the GPU busy at all the time, and we'll have to look at why. So here's just an example draw calls that we're going to do. Basically, the CPU here starts by creating one of these states. It builds a draw call. That draw call is then sent to the GPU, which will then draw it. As soon as it's sent, the CPU can then start creating a new draw call. Now, the thing here is that this GPU side of things takes more time. So we got a little bit time on the CPU where it has to wait for the GPU. What it can do then is actually step into the other course and say, I can help calculating the next frame. So it's not a bad thing. And when it's done, when it's ready to ship draw call 2, it can then start making 3, and it goes on like this. But suddenly here we get draw call 3. And in this case, the draw call is shorter than the time it takes to create the draw call, or the GPU side of things is shorter. What will happen then is that we get this starvation. The GPU needs to wait for the CPU with new instructions, basically. This will happen if you draw a lot of very small, simple objects. You will get these starvations. And this means that you're basically wasting cycles, because this GPU can't do anything during this time frame. And there are smart methods on getting around this, which we'll talk about. And we continue like this. So here we can see that basically this is a frame. Now, multiplied by 1,000. So 10,000 draw calls is not an odd thing today in a frame. And let's look closer at how a frame is being rendered. I'll skip a little bit fast through this. We got zombie here. what would happen if we put him through our generic pipe? So first, frame preparation. We need to calculate physics for him. We need to do an animation state. If somebody's supposed to shoot him, we need to have that. Audio, make some scary zombie sounds. AI, obviously, not that much, zombie. And some scripts, whatever game needs to run around this. And this will eat a little bit time on our CPUs 2 to 4 here. And when this is done, this character has 2 materials. We have one for the face and one for the body. So this means that we will have to do 2 draw calls for the materials, and then we probably want shadows, so we'll add a 3rd draw call. And now we got this object on the screen. Even though we have an insane amount of power at our disposal, we hit bottlenecks. And this, I mean, pretty much anyone that made a game will at some point hit a performance problem. And that's what in big games leads to crunch. So I was a producer for a couple of games, and I know that the last 3-4 months it was basically all about optimizing the game to run. We were only targeting 30 FPS back then, but it's a lot of work, that time frame. So first we're going to look at 2 terms which you probably heard. Here, how many here have heard CPU bound versus GPU bound? Just raise your hand. Okay, good, we got some here. Basically, there are 3 cases. This is a CPU-bound game. The frame preparation phase takes too long time. The frame rate is gonna drop. We got too much to calculate in a frame. This is also a CPU-bound situation. We get too many draw calls. So it'll take too long time and the frame rate will drop. This is a bit of a contrived situation, but it can happen. This is a GPU-bound situation where you actually have too much to draw. You have very few draw calls, but too much to draw, and now you're GPU-bound. So let's make a game. We pretty much laid the framework of where we are and how we're going to apply this. So we're going to make a zombie game, and I just put in a lot of different things here just to show like we're going to push the limits. We're going to have hundreds of zombies, awesome weapons, kick-ass graphics, beautiful, bad, scary environments. We're going to have everything destructible, like every game started. 4 players, of course. Oh, boss zombies. And of course, it needs to run in VR, which means we need to hit it at least 90 FPS. So let's say that we just stupidly make this game. We just combine everything, we press build, and we realize that, oh shit, this is what it looks like. Everything takes too long time. We're fucked. Well, let's take a look at what we can do here. So obviously, a lot of the work when it comes to optimization is done in code. But for the sake of the rest of the presentation, I'm going to focus on what you can do with 3D assets to kind of better the situation. So first, we got to see how we can reduce the time it takes to prepare a frame and what we can do with 3D assets on this. Actually, not that much, but some. So, I mean, the obvious thing is bullet tracing. If we have 100 zombies there and we have 4 players and there's a lot of weapons and stuff, bullet tracing is probably gonna eat a lot of time. And if we have high-res meshes for our zombies and calculate our hits on the zombies with that, it's gonna eat a lot of time. So we can make a simplified version of the mesh that we can calculate hit bullet tracing for. So that one would probably save us quite a lot of time in this kind of situation. So we saved that a little bit there. The second thing is the animation state. Now, when you're looking at the animation state on the frame preparation side is not for looking good. It's just so that you know how the character is positioned when you're shooting it, so that you can do correct tracing. This means that you don't need to calculate all the fingers, facial bones, everything. You might need just the big ones. So if we can simplify the skeleton, we're once again gonna save quite a lot of time if we can calculate towards a simpler skeleton. Another thing, of course, collision. We can make cheaper collision geometries that will make collision basically cheap. That's going to cost a lot in this kind of situation where we've got 100 zombies. The cheaper collisions we can do, the more we'll save. And that's going to save us some. But this is about as far as we can get. I was trying to figure out more stuff that you could do. There's probably something else, but to be frank, on the frame preparation side, most of the work has to be done in code, or possibly even cutting content. But let's say that we do a lot of work in the code, and we did it. Yay! Cool. So we solved the first bottleneck, but okay, we got too many draw calls. So let's go dig. Now we got to check what is causing draw calls. And here is where you can do a lot with 3D asset to actually gain time and performance. So one of the obvious ones is, as I told you, each material will cost a draw call. One very obvious thing is the zombies here. They had 2 atlases, not very different materials. What if we just pack them into one atlas? Now we got one draw call for the zombie, significantly faster. So let's say we do that even when they're a little bit further away, and we can also simplify the shader at this time. Boom, we're gonna get a lot of draw calls there. So object count reduction. Now, as I said, the basic rule is that one object will cost 1 draw call. There are techniques how to solve this in code, but if we're applying that method, we're looking at this gold mine. This gold mine consists of a lot of different rocks and other types of objects. This is going to be quite a few draw calls if we draw that one. This is a turbo squid asset. I think it's about 110 draw calls or something like that. Now, what you can do is just combine all these objects into one. You use high-res meshes, you combine them into one, and now you got only 1 draw call for this object, and you saved a lot of draw calls if you apply that in many places. So by doing this a little bit here and there in the game, suddenly we reduce the draw calls by some more. Once again, material merging for static objects. We're packing up, here's a vehicle, it has a bunch of different materials. We'll just combine those into one atlas to 1 draw call. And if we do that all over the game, we're gonna save some more. Now, if we're using long view distances, we're going to have a lot of objects that are far away, that even though we might have done simplifications to them, we need to bake them into one object. So this is an approach that, let's say this city block, it's a lot of different houses, but now we're a couple of 100 meters away from that. What if we just combine them into one object and build one simple object that we replace when we're far away? That way we're taking away a lot of draw calls from the background and can focus that on the things that are close to us. So large group merging, also called age LOD in UE4 for those using that. With that being done, we save some more. And then of course we can also do occlusion meshes and use occlusion to colorway, basically cheap Z-pass pre-filling to colorway some objects. So here we have a cheap object, and that tells us that we don't need to draw the objects that are behind it. But this depends if you have support in the engine to use this kind of technology. And with a little bit of that, we end up close to the goal, and a little bit of more random work, taking away some, and we getting there now. Yay, we made it. Now here comes the situation where it's a little bit tricky. This is actually probably never going to happen in today's situation. With DX11, you're very likely to never ever see that you are GPU bound. Whereas with DX12, it's going to open up the GPU bound situation again. Because what will happen, the process right now, since it's basically been that the draw calls and the GPU side of things, they walk hand in hand. And it's basically like this hamburger place. So we got the guy there to the left. He's flipping burgers. And he's passing those burgers over to the guy to the right. Basically, he's sending draw calls like flip, flip, flip over. As a customer, all I care about is that I get my burger, it's good, and that it's pretty fast. Now, I'd probably look at the guy at the GPU and say, oh, it's coming out too slow. Whereas in reality, it might be the guy flipping the burgers that takes too long time if I optimize this chain. But it's hard if you just look at it. You probably have to start counting how fast this thing's moving. And it also depends, well, here's this, sorry, I'll go there. It also depends on what kind of burgers you're making. If you're making a very advanced burger with a lot of condiments and stuff on top of it, it's going to take a long time to prepare that burger. Whereas if you're making that kind of McDonald's, boom, it's not going to take that long time. In the game world, the comparison would be if you use very advanced shaders, you're more likely to become GPU bound. Whereas if you use simple shaders, if you're have very few and simple shaders, you're more likely to become CPU bound. But no matter what, even if you don't come in the situation where you are GPU bound, it doesn't hurt to save time on the GPU if you can. That allows you to, at the end of the game, rather add some cool post effects or beef up the look rather than have to shaving off in the end. So here are a few techniques that you can do. So first, I'll need to explain a topic. Like most of you, how many here have heard of or haven't heard of the term LODs? Okay, LOD, level of detail. Basically, in the past, the reason why you did LODs was mainly because you couldn't push as many polygons as you liked through the GPU. It was kind of bound, the pipeline there. Nowadays, that's not true. You can basically push millions and millions and millions of simply shaded polygons. However, what's happening today and what's making you GPU bound is the fact that small triangles are expensive to render. And I'm not going to go too technical on this one, but basically how the GPU is structured. It is structured in a way that rendering large polygons are significantly cheaper than rendering very small ones. You really don't want sub-pixel polygons. You want polygons that covers many pixels. In this case, I'm simulating, or we're kind of painting a situation where the GPU likes to draw polygons or pixels 2 by 2. So what you want, the reason why you do LODs, is that you want bigger polygons on the screen. This will make shading cheaper, and when shading is cheaper, it will save you time on the GPU. And here we can see a kind of an example of that. On the left-hand side, we have a highly tessellated model. And as it moves away, we can see the cost of shading these pixels are going up. Red is bad. On the right-hand side, you have a coarsely tessellated object. And as it moves away, you can see that the cost of shading that object is significantly smaller. And we have a LOD chain on that one. So the reason why you're doing LODing still is not you want fewer polygons, even though you save a little bit of time on that as well. But The main thing is you want larger polygons. So let's make some LODs. We do that. And this will not cut away individual draw calls, it would just make them a little bit shorter. Our shading becomes cheaper. We can also reduce animation cost. This is when we make LODs, it's really stupid to calculate fingers, face, and stuff like that when you're far away. So what if we just stop calculating anything below here and anything below like the feet and face when you're far away? Doing that will also save some time on vertex shading. So that too will cut down the amount of time we spend on the GPU. Shader simplification. In this case, we got the skin shader, typically one of the most expensive shaders in a game. Subsurface scattering and a lot of other effects makes skin shading very expensive. Funny story there, in Assault on Dark Athena, we had quite significant problems with performance at one point. And we're trying to figure out what it was, and then we realized that our character artist thought our new skin shader was so awesome that he put it on everything. Everything had skin shading, and we were like, wait, because they didn't know that it was extremely expensive. And to be fair, skin shading is useful not very far. I mean, a lot of those effects disappear when you get a little bit away. So you can replace that with a cheaper shader, and that will make the draw cost go down a little bit more. Now, let's get to this part. So I mentioned about starvation. How can we manage to efficiently use the GPU? Basically, don't have it in starvation mode that much. Well, this is actually detective work. This depends on what kind of tools you have in the engine to kind of figure out where do we have very, very small draw or rasterizations on the GPU. Now, in the example I showed you, this is a very possible candidate. If we had that gold mine with all those small objects, it's probably going to be quite costly. So we have two different solutions there. One solution, combine, which we already kind of explored. The other one is to batch things together, basically burn the objects into world position and render them in batches. So all the stones are rendered as one because they have the same material, and all the golden nuggets are rendered as one, same material there too. And then we have a cheaper object. So these are two different techniques, and I know that static batching is quite common. But if we don't want to do this, I mean, we might as well make it the prettiest gold mine ever. We might as well use that time so we can make those rocks bigger, because it's not gonna waste anything. It's just, time available to do whatever you want. So let's say that we magically get this done. We go through and we find these small objects that puts our GPU in starvation, and suddenly we got this. In this phase, we probably reduced our draw calls a little bit as well, because they would kind of go hand in hand here. So yes, we did it. We can press ship game and go on to the next one. Summary. So, an overview. What my purpose here was to give you all an idea of what the generic render pipeline looks like. Basically, rendering a game in most situations would look like this. You have the frame preparation, you have the draw call sending, and the GPU does the rasterization of the draw calls. The frame preparation is done on the CPU. It calculates what will happen in the frame, and it's extremely computation expensive. I mean, we have a lot of cores at our disposal, but it's still quite common that you are CPU bound here. Draw call passing is done also on the CPU. It creates a state that is passed to the GPU. Each draw call is roughly a fixed cost. There is just, you can pretty much know how many draw calls you can do in a frame given a certain frame rate. Rasterization is done on the GPU. Rasterizes the draw calls to the screen. And the cost is well dependent on how complex your models are and how complex your shaders are. And you should always try to keep the GPU busy. And basically, to wrap it all up, to kind of make you picture here, it's optimizing a game is like running a hamburger joint. I mean, your goal is to get out good burgers fast. And this is kind of the point. You have to find where are our bottlenecks so that we can provide our customers with burgers faster, basically. Yeah, basically that's it. Thank you for your time.
Hey Samuel, thanks for the presentation. I'm just curious, what tools can I use to gather information like this? Well, to know what to fix and where I can reduce this.
To be honest, I'm not an expert on what tools you have in Unreal and Unity. I know, I mean, for example, for GPU starvation, you have specific tools for the different brands of GPUs. I know that Intel has VTune and things like that. But actually, I'm not an expert on this. This is the tricky part. Like, it depends on the engine. But getting an idea of what you can do, it's another topic, like how do you actually do this? I just want to give people an understanding on what you do and why you do it.
Yes, thank you for this.
Yeah, sorry.
More specific information about DirectX 11 and DirectX 12. What's the core differences and why DirectX 12 is going to be able to bottleneck current GPUs?
Well, once again, I'm probably not the best expert at answering this question, but DirectX 12 will allow you to pass make draw calls from several threads on the CPU, which means that it's more likely to put the GPU under a heavier strain, which means that you can draw more draw calls. The funny thing is that throughout times, we've said many times that, oh, now this new thing comes, we're never going to have to optimize our game again. Like, when we got, I think it was Xbox One, like the first Xbox. It was pretty good actually back then. It felt like we got a lot of memory now. Well, it was 64 megabytes. It took like a half a year and we surpassed that. When Xbox 360 came, that was like a huge leap. It was better than most of the PCs that came out there. Then everybody said, like, okay, this is just too much. We can do whatever we want. It took half a year, and then we're like, oh, we're out of memory, we're out of performance. And then Xbox One and PS4 came out, and they were kind of underperformed. So that was like, well, we got 8 gigs of memory. People are still running out of memory, even though we could run at 512 in the previous one. Now DX12 comes out compared to DX11. It's a pretty big difference in what you can do, but it will only shift the bottleneck to another place. That's the big difference. We'll still fill stuff up, mostly because we're a little bit lazy. Because we're like, okay. I mean, if guys making games in the 90s would look at what we do today, they would say, guys, how can you spend 8 gigs of memory? It's like crazy. We could send the whole Earth to moon with that amount of memory. So it just shifts where we have to spend our energy. Hi, welcome.